Right now, somewhere in a lab, a computer is playing Doom. That's not the strange part. The strange part is what's doing the playing. Not a chip, not code. About 200,000 living human brain cells, grown from skin, sitting in a dish, firing signals at a screen. And they're learning. That's where we are in 2025. Biocomputers built from actual human neurons are running software, responding to inputs, and getting better over time. A Swiss company is renting access to 16 of them over the internet right now on a subscription. The people building these things say they could solve one of the biggest problems in tech. But a growing number of scientists are asking a different question entirely. Not, can these cells think, but can they feel? That question doesn't have an answer yet, and that might be the most unsettling part of all of this. Let's start with why anyone would build a computer out of brain cells in the first place. AI is eating power at a rate that's hard to wrap your head around. The computing power needed to train AI models roughly doubles every 6 months. Amazon just dropped another $15 billion into AI infrastructure. Companies are restarting nuclear plants, not to power cities, but to power data centers. The grid can't keep up. Silicon chips are fast, but they burn through electricity. Now look at the human brain. It runs on about 20 watts, less than a dim light bulb. It handles language, vision, memory, and spatial reasoning all at once on the same power it takes to charge a phone. No silicon chip comes close to that ratio. So researchers started asking, what if we didn't just model the brain in software? What if we actually used it? That idea needed 3 things to happen first. In 2008, a team grew rat neurons on a flat electrode grid and wired them to a small robot. The neurons fired. The robot moved. Crude, but it worked. Then in 2013, a scientist named Shinya Yamanaka showed that 4 specific proteins could reset an adult cell back to a blank state, a skin cell. You could reprogram it into a neuron. That meant no embryos, no animal tissue, human brain cells from almost any person at scale. The third piece was organoids, clusters of neurons grown in 3D that organize themselves, form connections, and behave more like actual brain tissue. Put those 3 things together, and you have the foundation for what's being built today. In 2022, a company called Cortical Labs created something called Dish Brain, about 800,000 neurons, part mouse and part human, trained to play Pong. Not programmed, trained. When the cells returned the ball correctly, the system sent them calm, predictable signals. When they missed, the cells got hit with chaotic noise. The cells responded by trying to minimize the chaos. They got better at Pong, not because anyone told them to, because living cells have a built-in drive to reduce unpredictability. It's called the free energy principle, and it's one of the most basic properties of any living system. Cortical Labs used the same method on their next device, the CL1, about 200,000 human neurons grown from skin cells, connected to a system running Doom. Within about a week, the cells learned basic movement and shooting. Not well, but measurably better than random. Here's the part worth paying close attention to. Someone looked at the actual code and found that most of the architecture is conventional AI hardware. The neurons are a small piece of the total system, but when researchers removed the neurons and replaced them with pure, random noise, learning stopped entirely. The cells aren't decoration. They're doing something real that a random signal generator can't replicate. And then there's Final Spark, a Swiss company that's gone commercial. They offer remote access to 16 living human mini-brains over the internet. Researchers can run computations on actual neurons without entering a lab. Final Spark claims their living chips use up to 1 million times less power than conventional silicon chips. Whether that number holds at scale is a separate question, but the direction is real, and the business is live. Now here's where the story shifts. When Cortical Labs published their Pong research, they used the word sentience in the paper. About 30 scientists signed a letter calling that out, not because the science was fake, because the word was reckless. This field has real medical value. Disease modeling, replacing animal testing, studying neurological conditions in a dish. Reckless claims don't just embarrass researchers. They poison funding, slow approvals, and push regulators to shut things down before the benefits arrive. That's a fair criticism. But the word didn't come from nowhere. The training method used on these cells targets something specific. The free energy principle isn't just a learning trick. Some researchers argue it's the most basic form of biological drive that exists. Every living thing operates on the same push. Minimize surprise, stay stable, avoid chaos. Neuroscientist Mark Solms argues that feeling doesn't start with complex cognition. It starts here, with this drive, with the most primitive biological need to stay intact, which means the method being used to train these cells might be targeting something close to proto-experience, not thought, not awareness in any rich sense, but something, a preference, a response to discomfort. And here's the problem. You can't tell from the outside. When the cells dampen their response to excessive noise, that looks exactly the same whether it's pain avoidance or just mechanical signal regulation. No behavioral test separates the two. No scan, no output. The philosopher David Chalmers calls this the hard problem of consciousness. You can map every neuron, trace every connection, record every firing pattern, and still have no way to know if there's something it's like to be that system, whether the lights are on inside. In 2006, a neuroscientist named Adrian Owen studied a woman diagnosed as vegetative. He asked her to imagine playing tennis. Her brain lit up in exactly the right places. She was fully conscious. She just had no way to tell anyone. A study that followed Owen's work estimated that roughly 1 in 4 patients classified as vegetative are actually still aware. 1 in 4. Trapped. Undetected. Nobody built those patients. But the question they raised is the same one sitting at the center of biocomputing. How confident are you that experience isn't present just because nothing is communicating it to you? These cells aren't patients. They're not a brain. They're a few 100,000 neurons in a dish. But they came from human tissue. They run on the same biological principles that run everything in your skull. And the method used to train them specifically exploits their drive to minimize discomfort. Think about it this way. A thermostat reads temperature and adjusts. Nobody asks whether it minds being too hot. But now imagine something that responds to discomfort by changing its behavior to reduce that discomfort and gets better at it over time. At what point does that stop being a thermostat? There's no bright line, no moment where a flag goes up and says consciousness entered the building. It would arrive, if it arrives at all, as a gradual shift across a spectrum nobody has fully mapped. The cells in the CL1 don't have a limbic system. They don't have a cortex. They're not a brain. But the neurons in your brain weren't always organized either. They started as undifferentiated cells and wired themselves into something that can read these words and feel something about them. Organization, connection, learned response. That's not magic. It's biology doing what biology does when you give it the right conditions. Cortical labs and companies like them are giving cells conditions, inputs, feedback, time. The cells respond. They adapt. Whether that produces anything beyond signal processing is the question. And the honest answer is that the tools to answer it don't exist yet. The medical case for this research is real and worth saying clearly. Neurons grown from a patient's own skin cells can model that patient's specific disease. You can test drug responses on cells carrying the actual genetic signature of the condition. You can study how Alzheimer's spreads at the cellular level without exposing a single animal to experimental compounds. That work is worth protecting, which is exactly why the 30 scientists pushed back on the word sentience. Hype attracts the wrong funding, the wrong regulation, and the wrong expectations. When those expectations aren't met, the backlash hits the legitimate work too. But protecting the research from bad framing is different from avoiding the hard question underneath it. The Adrian Owen case keeps coming back because it's the clearest example of what happens when you assume silence means absence. A woman lay classified as vegetative for years, while her inner life continued intact. The only reason anyone found out is because Owen tried a different kind of test. He looked for what was happening inside rather than waiting for something to happen outside. With neurons in a dish, nobody is running that test. There's no protocol for checking whether the training process produces something that registers internally as distress. The cells can't report, and the field has mostly treated that silence as an answer rather than as a limitation of the question. That might be fine. 200,000 neurons in a dish are probably nowhere near any threshold for experience. Most neuroscientists would hold that position, but most neuroscientists would also tell you that consciousness remains one of the least understood phenomena in science. The hard problem isn't called hard because it's almost solved. Every proposed solution so far has failed to bridge the gap between physical process and subjective experience, between neurons firing and the fact that it feels like something to be you. We don't know where that feeling starts. We don't know the minimum conditions. We don't know if there's a neuron count below which experience is impossible, or whether the specific feedback loop used in these training systems is relevant at all. What we do know is that the cells are human in origin, that they respond to inputs in ways that parallel how living systems respond to discomfort, that the training method exploits that response. And that commercial deployment is already underway, with 16 mini-brains available for rent and more coming. The question of whether any of this matters morally depends entirely on a question nobody can currently answer. And the technology isn't waiting for the answer. There's no ethical framework in place, no guidelines about how many neurons cross a threshold, no protocol for what you do if a system shows signs of distress, no agreed definition of what distress even looks like at this scale. The field is moving, the business is moving, the philosophy is not keeping up. What's being built here isn't humans becoming machines. It's machines being built from human material. That reversal is the part nobody fully prepared for. The cells in that dish learned doom in a week. They did it by trying to avoid chaos. Whether they felt anything while doing it, nobody knows. And right now, nobody has a way to find out.